Well, this is a different problem here. Question 5 on our angular momentum handout. You've got a student, 42 kilograms, at the center of a merry-go-round, radius 3.4 meters, and a moment of inertia of 840, and it's rotating at 1.8 radians per second. She walks to the outer edge, of course, which changes the distribution of mass in the merry-go-round, increases it, right? You can have more mass far from the axis of rotation. What is the angular velocity of the merry-go-round as she reaches the outer edge? Now, since there's no torque exerted on this system, the total angular momentum before equals the total angular momentum after, and that's this right over here. So we know the moment of inertia before, and we also know the angular rotation. I have the units wrong over here. It's radians per second. Okay, this is actually wrong. Let me fix it. Radians per second. And that equals the total angular momentum after. We need, what they're looking for is the angular velocity after. We've got to find the new angular moment of inertia, rather, after the student walks from the middle of the merry-go-round, where she technically applies some moment of inertia, but I think they're assuming since she's in the middle, she contributes no moment of inertia because she's at the middle of the merry-go-round. So the final moment of inertia is the initial, 840 kilogram meters per second, which we were given, plus mr squared, the result of the student, 42 kilogram student, walking out to the radius, which is 3.4 meters, but that gets squared. And so in walking out from the middle to the edge, she adds a new, adds a little bit more to the existing moment of inertia. I'm going to calculate this now. And you get a new moment of inertia of 325.52. That's kilogram meter squared. Remember, you can leave out that radians, which always I find funny and weird, but they do it, times WF. So we'll divide both sides by that 1325, and you get 1.14, which turns out to be 1.1 radians per second. So just to summarize, you've got this person in the middle. She walks out to the edge, thereby increasing the moment of inertia of the merry-go-round, but the total angular momentum before equals the total angular momentum after. And no surprise, by walking out to the edge, she increases the moment of inertia of the merry-go-round, which decreases rotational velocity from 1.8 to 1.1. Let's look at another one. A ball whose mass is 0.14, attached to a string of length 0.64 meters. That becomes an R because it's spun in a circle with this angular velocity. What is the angular momentum? That's I times W. It's a simple, we have to actually calculate the moment of inertia, which is the sum of all the mr squared. There's a single m, there's a single r, and the W we were given, so it's just a plug-in. The mass was given as 0.14 kg, and the r that was given as 0.64 meters. We square that, multiply by the W that they give us, radians per second, and then you multiply it together and you get, let's see, I like to do this, so it's 0.64 squared, I do that first, times 4.9 times 0.14, and you get, oh good, 0.28 kilogram meter squared per second. Simple. So when something's swung on a circle, it's one of those moments of inertia you have to calculate using that sum of the mr squared, which is I and W is given. Here you've got a platform rotating at 22 revolutions per second. You know, we have to fix that. Person standing in the middle, arms at his side. He extends his arms. Of course, he's going to increase his moment of inertia, and he slows down, no surprise, from 2.2 to 1.4. What is his final moment of inertia in terms of the original? You know what? We actually don't have to cancel this out. Let me see if I'm right about this, because I think, watch this. I'll show you. You don't have to really cancel out. Sorry, you don't have to change the revolutions per second. I'll show you why. So you have a moment of inertia, okay, that we'll just call I because nobody told us what it was. We have initial angular velocity of this, and you have a final, which this is a mistake because this should be final. That you want to find the final in terms of the initial. We know that it turns to 1.4 revolutions per second. And I told you we don't have to convert these because they cancel out. And the final, divide both sides by 1.4, 2.2 divided by 1.4. Any ratio, things cancel out, and turns it to be, so 2.2 divided by 1.4 is that the final moment of inertia is 1.571 times the initial. So the final moment of inertia is 1.57 times the initial moment of inertia. When he stretches out his hands, he of course increases his moment of inertia. Let's do this one. I'll be a roller skater. She's spinning at 1.5 revolutions per second. Model her after a cylinder with a mass of 0.85 and a height of 1.8 and a radius of 0.18. What are we looking for here? What is the angular momentum of so this is a plug-in. Angular momentum, which is L, is I times W. And she's supposed to be modeled after this equation for the moment of inertia. And her W is 1.5 revolutions per second. Of course, that's an issue. Let's convert right here. 1 revolution is 2 pi rad, and then we get to convert it there. So we've done something like this before. So this is just a plug-in. 1/2. Her mass is 81 kg. Her radius is 0.18 meters. That gets squared times 1.5 times 2 pi. I'm just going to put the numbers in here so I'll calculate it out. 1.8. So it is 12 kilograms, meter squared per second. This one, I'm going to leave this one for you to do for practice.